Hello community, so great that you are back. Today I will improve my 3B AI model. Let's have a look. And you know what? I will do it for better causal reasoning, and we will discover here a new framework, and our work will be based on 2 new AI research papers. So you might say, hey, why a 3B model? No, you have to go for the big one, no, for the 405 billion free trainable parameter model, no? Or you say, okay, I then have to go with the distilled version, and from the distilled version, maybe I go then with the integer quantized version, and then if they are two, no, no. And you say, what? Does size not matter anymore? Welcome. I will show you here a new study where we find that the Q when 3B far exceeds a llama 3B under the identical reinforcement learning training. And this will open up a complete new box of Pandora, and we will have to answer here what intrinsic language model properties will enable here a self-improvement for advanced AI reasoning. So let's start. A new framework inducing and really important stabilizing here an extended reasoning process in our language model by, now we leverage here a lot of elements. We will have a look at supervised fine-tuning with a detailed chain of sort data. We will have a new reinforcement learning with a new carefully designed reward function, and we will have to have access to new data sources. And all of this together will lead to some substantial improvement in the model performance on complex reasoning tasks. So, you see, we can do this on a 3B model. Yes, we can. So let's start right now. And I would say, hey, wait, you are not trying to trick us here. No, this is not going here from a PPO here to a group relative policy optimization like everybody else is doing here on YouTube. Of course not. Because if you want to learn about this, I would say, hey, go to Hugging Face. They have a beautiful article here, published February 7th here, understanding here PPO and GRPO differences. And you might say, hey, wait a minute, so you publish, now I know, the value optimization, no, because we have a PPO collapse in long chain of sort, no? And this is the solution you presented to us. Yeah, beautiful idea, but no, this is not what I want to talk about. I want to talk about a new framework to induce and stabilize here an extended reasoning process in our language models, especially small language models. Because we understood from this beautiful video here, there is no emergence of intelligence. There's no super intelligence, no general intelligence. AI logic in our LLMs is simply pattern-based. So therefore, we will go here this classical route and introduce 4 new logical patterns in our models, vision language model, large language model, foundational model, reasoning model, whatever you want, for improved reasoning. So it will be a simple logical procedure. So let's synthesize now 2 lines of AI research we will bring together today. Because, hey, we want to have a little bit of fun. It should not be a boring video to enhance here the causal reasoning here in our large language model. So we have 2 new ideas. We have here extended chain of sort reasoning here, stabilization here for the long chain of sort trajectories, because otherwise the model will collapse. We have areas of massive instability. And then we will have a look at structured cognitive behavior for self-improving reasoner, and I'll show you here 4 prerequisites for a better reinforcement learning of our little 3B model for causal reasoning. So you see, it is not the size, it is not what you think, it is something completely different. Something is hiding behind the data, and something is hiding behind the algorithms. And maybe we use the wrong algorithms. So let's explore this. For my green grasshoppers, really easy. We will have a look at how to stabilize here long chain of sort, so there's no instability anymore in the projects or in the models. And then we add 4 new logic patterns here, especially here for the long chain of sort causal reasoning. That's it. If you want to have here the study, here this study is a beautiful study by Tsinghua University and Carnegie Mellon University, and this here is by Stanford University. Let's go. So if we open up now our box of Pandora, you know what we are doing. Yeah? We have the pre-training, the supervised fine-tuning, the reinforcement learning, and then we have all these beautiful reasoning models, no? 01, 03, R1, whatever, where we have test time compute scaling here, and we just wait 20 seconds to 5 minutes, and it's great. And at first we will have here new discovery that the reasoning behavior in the base model, this is essential for all the further improvements we can do via reinforcement learning. Plus, for the long chain of sort reasoning, we will examine 3 conditions where this extended chain of thought reasoning, when does it really emerge? Then we'll look at the scaling behavior of this long chain of thought with an increased inference compute or test time compute, and then the impact of the reward design in our specific reinforcement learning. And we'll find out the classical reward models, the classical oral models are not optimal. And you know what? At the end of the video, you will understand that all of this will depend massively on the pre-training data of our language model. It's absolutely fascinating. So, long chain of thought. To describe here an extended sequence of reasoning token that also demonstrates a more sophisticated behavior. And we are looking here at 4 new elements: branching and backtracking, the error validation, and the correction with self-correction. So it's easy. The model systematically explores your multiple paths. You notice from Monte Carlo tree search, it's branching out. And it reverts to earlier points if a particular path proves wrong. This is what we call backtracking. Then the model detects inconsistencies or maybe mistakes in its inherent, in its intermediate steps, and takes corrective action to restore coherence and accuracy, error validation, and correction. So what we have is a reinforcement learning procedure that has emerged as a crucial method for developing those capabilities. Yet, as the authors here from Carnegie Mellon show us, the conditions under which those long chain of thoughts emerge remain unclear. And we will examine this today. And the reinforcement learning training requires here some careful design choices, particularly the reward function that you will choose here. This is the crucial element. And then we will go and have the scaling test time compute. This also enhances the reasoning in our LLMs. And you know this from our OpenAI 01 or 3 or 1, whatever you have. With long chain of thoughts, enabling now strategies like backtracking and error correction. So you see both studies are really on the same topic. The first one examines here the condition under which this long chain of thoughts emerge and how we can make build a stable AI system. And then we have a look, what are those elements for this long chain of thought? What are the key elements? What are the most important facts? And we have 4. Yeah. So you see, we're working on both sides here of the training compute and the test time compute scaling. And I know some of you might say, hey, TTS is the old abbreviation for text to speech. Yeah, this was old, gone, past. We work with test time compute scaling. So let's have a look if we have today maybe the chance of having a spark of genius. So let's have a look. Reasoning capabilities. The reasoning capabilities in AI system tend to emerge here with increased training compute. We have to wait a minute, 3 minutes, 5 minutes for O3 or O1 Pro to finish. But their development of these capabilities is not guaranteed, making here the reward shaping crucial for stabilizing here long chain of thought, their length growth, because they might collapse and just produce nonsense. So if you think you have here a reasoning model and it's always working, oh, no way. Second, and core abilities like the error correction that I showed you are inherently present in some base models. I will show you 2 base models where we have it and a base model where it's not in the training data. But incentivizing these skills effectively for the complex task via reinforcement learning demands some significant compute. Now, the emphasis is placed on how supervised fine-tuning with long chain of thought data improves now the subsequent gains that we will achieve if we add reinforcement learning. So you see, it all works together. It is all intertwined in a beautiful complexity. So let's have a look at supervised fine-tuning with long chain of thought data. Normally, all the problems that you know, we have short chain of thought data. But for some really complex topics in mathematics, in physics, in chemistry, in science, wherever you are, we need longer reasoning chains. So in our paper, the researchers generated here some high-quality long chain of thought data with master models, what they call this, QWQ, 32B preview, and a rejection sampling technique. And this data, this training data, is then used to train here the base model. Great. And then if we have the supervised fine-tuning model here, this is now our critical, if you want, initialization state, where we then can add reinforcement learning. So another central hypothesis is that supervised fine-tuning, using here the long chain of thought training example, create here a real good starting point, a real good beneficial initialization point for the reinforcement learning process. And this initialization in turn makes subsequent reinforcement learning much more effective. I'll show you the figures in a second, compared to starting here with a raw base model or with some short chain of thought reasoning chains. So you see, the core idea is rather simple here of this paper here by NEI, Tsinghua University and Carnegie Mellon University from February 2025. And they say, yeah, the condition under which this long chain of thought emerge on a stable form, this remains unclear. So if you think you know about long chain of thoughts, well, think again. And then if we apply some reinforcement learning training, the alignment, this does not work with the normal oral training procedures that we have. We have to modify our reward systems. Great, no? But it's simple. It's really simple. So let's have a look at this. At first, the supervised fine-tuning for this long chain of thought data generation. I've showed you we have some high-capacity teacher model. They generate here high-quality reasoning traces, and we will use this training data. And they tell us, if you compare this, the supervised fine-tuning with this long chain of thought data against a supervised fine-tuning with the short chain of thought data, the results in all their mathematical benchmark and whatever logical benchmark demonstrate that the long chain of thought supervised fine-tuning scales to higher performance. So it's better to have, for more complex topics, the long chain of thought supervised fine-tuning. And then if we have the supervised fine-tuning checkpoints, you know what we're going to use? We use them for the initialization for the reinforcement learning optimization that takes now place. So models are further tuned, aligned using reinforcement learning, PPO, starting here from supervised fine-tuning checkpoints. And what we need, and I give you the solution, you can have the exploration here in the paper, but I just give you the end result. We need a new reward function. We need a cosine reward function. This is interesting, but it has a very specific form. And you know what? I just show you this and you will immediately understand. So the classical reward function in the easiest case is 0 and 1. And with the cosine reward function, if you look here, you see exactly the form and the function of this cosine reward function that achieves what we are looking for the long chain of thought case. Now, if you look now at the performance data, and this is all here in the study, and you find it here. So again, two types of chain of thought data are compared. The short chain of thought, this is what you know, this is the conventional. These are the concise reasoning traces. And then we have the beautiful long chain of thought data, extended detailed reasoning trajectories, distilled here for mathematical problems here from high capacity teacher models, using rejection sampling techniques and some other advanced techniques to really get the best reasoning traces here, but the long form reasoning traces for real complex topics. And yeah, they show this here for different benchmarks. You see here 4 benchmarks. The only thing that I would like you to remember is in blue, you have the long chain of thought performance, and in orange, you have the short chain of thought, and this is done on a Llama 8B. And if you do all the supervised fine-tuning tokens and the reinforcement learning, you see here the accuracy, the performance. Blue is always better. Great. All the details in the study. So let's come to a summary of our first study. What have you learned? There's a significant performance improvement of our model if we go here a specific route of supervised fine-tuning and reinforcement learning. The model fine-tuned, supervised fine-tuned with the long chain of thought data achieve a high accuracy on mathematical benchmarks compared to those using here the shorter chain of thought data. And when those models are further optimized here with RL, additional gains are observed. For this reinforcement learning, we need here a specific cosine reward function that is really simple, as I've shown you, to stabilize here the growth of the chain of thought length, preventing here runaway repetition, and ensuring that additional reasoning steps contribute meaningful to the answer. Because what we have is some system just to go in a loop or just produce nonsense content to fill up here the form. So we have now a much better downstream performance and a more controlled, complex reasoning process. So this RL alignment from a long chain of thought supervised fine-tuning initialization outperforms all the other reinforcement learning methodologies from the base model by a significant margin. You have all the data here in the study, emphasizing here the importance of structured reasoning patterns as a starting point. You might say, hey, so what is now important? The structured reasoning patterns. And you say, yeah, but if I really want to have here just a single most important thing, the structured reasoning pattern, or the most important fact. Talking about facts, let's come to the second study by Stanford University, March 3rd, so just 2 days ago for me. And they say, we find, you remember this sentence from the beginning of my video, that QN3B far exceeds here the performance of a Llama 3B under the identical reinforcement learning training methodologies. Why? Now Stanford can give us an answer. Imagine, in March 2025, finally we know why Llama is not performant at all in complex reasoning tasks. And they use here a mathematical puzzle, and in this mathematical examination, they know there's a countdown game, and yes, this is the environment, but they looked here for some specific behavior, why Q1 is better than Llama. And they said, what are the key to unlock here the self-improvement in the reasoning process? You're not going to believe it. They found here 4 topics: verification, backtracking, sub-goal setting, and backward chaining. Sounds familiar, isn't it? So this self-improving AI reasoner study identified here our 4 essential, they call it a cognitive behavior. Now, since we are talking about AI machines, think about here an NVIDIA supercluster somewhere in the cloud, I don't know if I would call it a cognitive behavior. It's an AI behavior. So we have verification. The AI system just systematically checks here for intermediate steps. Then we have the AI behavior of backtracking that is now a pattern in its logical, if you want, template structure. This backtracking is revising and abandoning failing solution path. Then we have the AI behavior of sub-goal setting, decompose here a complex problem into manageable intermediate objective into smaller subtasks, and a backward chaining, working from the desired outcome back to the problem's initial condition. So those are now 4, if you want, logic patterns that we can real easily compute, define, and tell the system, hey, those are the 4 behaviors that we will train you on, that we expect that you perform on. And with those 4 systems, the reasoning performance of my 3B model will change significantly and outperform even a 405B. So the experiments performed now by Stanford University on the countdown, a mathematical countdown game, yes, so algorithmic planning and multi-step reasoning, and have a look at the literature. And they compared, as I told you now, this Q1 and the Llama 3B. Now, interesting, the Q1, given its training, showed those 4 behaviors. And Llama 3B, initially deficient in such behaviors. So, yeah, countdown, well-defined, mathematical constrained environment, planning, verification, source-like behavior, making ideal for assessing complex reasoning. Great, Stanford found here the environment to test it on. And then this found here Q1 naturally exhibit here a higher rate of the 4 targeted cognitive behaviors. You know, cognitive I think should be only human, but okay, let's go with an AI cognitive behavior. And Llama has a limited use of these strategies. So you see, we talk about the base models here, and there's the difference. So initial assumption is that the initial presence of cognitive reasoning behaviors, okay, in a model output is crucial for the effective self-improvement. And if a model exhibits this behavior as the Q13B does, so it's important which model you choose, it can leverage extra computation to solve more complex problems. So if I go with a 3B parameter model, I will not go with a Llama, I will go with a model that has in its pre-training phase been trained on those 4 behaviors. here you have now from the starter here the data, beautiful. Everything is here for you. Just want that you focus here on the core. You see here Q1 is, let's call it in pink, violet, whatever, and llama is here in blue. Here Q1 and llama is close to 0 in the response length. And if you look then, yeah, I have this here a little bit better. The behavior now explained here, and you have here the Q1, and you have here those 4 elements. I don't want to have it a cognitive behavior. There's 4 elements here of our logic pattern structure. So we have verification, backtracking, sub-goal setting, and backward chaining. And you see here in the steps here of our reinforcement learning that here we have with Q1, oh wow, there's something going on with verification and backtracking for logic. This seems to be really the system how Q1 is working, is applying in its reasoning process. And if we look at the llama model, also checking for those 4, you see everything flat line, dead at 0. So Q1s, if you want dramatic performance improvement, coincide with the emergence of specific behaviors, those 4, particular here, the verification and the backtracking, as you can see here in blue and in orange. And the llama models don't show any of those behaviors. So you see, it depends on the base model, which is absolutely fascinating. And then they said here, Stanford here said, hey, we analyzed here the baseline reasoning patterns in general. And you know what? We included now not only the 3B models here, but we go with a 70B model because size matters. Yes, of course. Well, it turns out absolutely wrong. Let's have a look at this. So we have here in, I don't know, Fleeter or whatever this color, you call it here, the Q1 base. And you see, really good. Outperforms everything else. Then in light blue, we have the 3B from llama. And for verification, it's almost nothing. Backtracking, almost nothing. Sub-goal, yeah, a little bit. And backward chaining, really nothing. And then for this 70B. Now this is, should you go with a 70B model for reasoning? Is this effective? Does it bring you more performance? Dark blue. Now compare this dark blue here to the Q1 3B model. Compare this dark blue to the 3B model. Compare this dark blue to the 3B model and this. And you see for the significant, for the important elements for causal reasoning that was identified for long, complex chain of thought reasoning task of your AI system, size does not matter. The llama 70B is crushed by a 3B Q1 because there are some inherent differences in its pre-training and in the basic and the training phase. So size does not matter anymore. And you know what? Going now deeper and trying to understand why is this happening. Stanford looked also here at the pure pre-training data set, and they said particular significant is reinforcement learning can only amplify particular behavior of the system that already is there. It's already detectable. Those behaviors appear in a successful trajectories. Of course, if you want to amplify or reinforcement learning here, the alignment optimization, if it's not there, what you want to align. So making this initial behavior that the system should have, like a Q&3B, a precondition for an effective learning process for mathematical reasoning. And please remember, we are here on a very limited spectrum of a game that is about mathematical reasoning and mathematical performance and mathematical causal reasoning with logical steps. So, reinforcement learning amplifies the behavior that are preconditioned for an effective learning. So, it depends on the pre-training stage. And a good 3B Q1 base model outperforms a 70B llama model. So, size, yeah, you know it. And then they said, okay, let's look now at the data sets that we have. Because if I want to optimize my 3B model, my local model, I need a good data set. And what are the best data set we have? Let's go with a pre-training data set. And I know a lot of my viewers wrote to me, hey, listen, I just take the model that are available for the big corporation. I don't want to fine-tune. I don't want to apply a reinforcement learning process. I'm just satisfied what I get for free. You can go with this. This is beautiful. But if you want performance, if you do it for a client, if you want to be here in a competition with others, you have to, as you see today in this video, to go to the supervised fine-tuning and especially to the reinforcement learning procedures to optimize your system for your specific task or the task of your client. If you just go here with models that are presented to you free of charge or you have to pay for O3 or whatever, it will not be the best performance system for your task. So let's look at the pre-training data. So really at the beginning. And they had a look here at this behavior of those four characteristics here in the pre-training data of the models. And you know we are here in mathematics and in mathematical reasoning and in causal reasoning. And they went here with, let's say, the most famous, the most important training data sets, OpenWebMath and FineMath. And you know what? They analyzed in this pre-training data or in this training data set, for whatever reason you use it, they found here, look, we are here at 0.02 in the distribution, how much we have in this pre-training data set. So they say, even in this mathematical focused corpus, the cognitive behaviors such as backtracking and verification appear, friendly formulated, infrequently, suggesting that the standard pre-training provides here only a limited exposure to this crucial pattern for reasoning. So in my words, all the standard datasets fail, do not integrate those four characteristics that that Stanford University identified here in its study, that this is essential for an improved reasoning process. It's not there in the training dataset. So guess what? The model, like Llama, will not show it. So you see, I think this open source, these small 3B models are so valuable for the research because we can run the research in base model, in fine-tune, in RL. We can experiment with this and we see that a 3B model has a significant performance in causal reasoning, outperforming the proprietary models. Great. So, you know what this means? This means pure frustration because it means we are back in the pre-training data. The quality of the pre-training data determine the complete behavior of the system for supervised fine-tuning, for reinforcement learning, for test time compute scaling, for advanced reasoning, for I don't know what. And yes, as I've shown you here in this video about the AI reasoning lie, we can build mountains here for the reinforcement learning. Huge construct, extreme whatever. You know where's the real cause that it does not work? In the pre-training data, in the quality of our training data set. So what we learned today, we can improve a 3B model extremely if we just provide the right pre-training data set to the model. It is not the size of the model. It is the intelligence and the insight, what we learned from all of this study, how to build the next generation of AI with the next generation of optimized pre-training datasets for logic, for causal reasoning in mathematics, in finance, wherever you work. And as it turned out, Q1 has it. Stanford tells us, hey, the Q1 3B has it. Llama, no. Interesting to see this perspective from Stanford University. So let's come to an end. 2 studies, and I've chosen these studies. I think I have looked at more than 70 studies about self-improving and reasoning here in the last month, and I've chosen these 2 studies for a particular reason. They have a beautiful intertwined insight. So don't just go for one study, combine it with a second study, and yes, I also had a third study in the background, but never mind. Those provide us here some beautiful insight. Both studies confirm that explicit reasoning strategies are essential for leveraging here our reinforcement learning to improve the model performance. And either we do it here as a cognitive behavior with our 4 elements, or as an extended chain of thought process. They are both here, they depend on each other, they need each other, and the insights from both studies supplement each other. Both work highlight here the increased test time compute and appropriate context window size that enables models to explore deeper reasoning paths. But be careful with the excessive length. Without proper reward control, this will lead to an instability of the system. And the system will just produce nonsense in its long chain of thought reasoning. Therefore, for those to circumvent these instability islands, if you want, proper reward control, and I've shown you here a particular new reward function that we should apply in our OL training procedures. Great. And this, let's call it integrated studies, demonstrate now that enhancing the reasoning in our language model requires both inducing here explicit cognitive behaviors as a pattern, because AI only learns pattern. There's nothing like the emergence of intelligence, as I've shown you. But AI is a pattern machine. So let's have these cognitive behaviors encoded in patterns and enabling this by extended chain of thought reasoning. Those 4 behaviors, as identified by Carnegie Mellon University, were verification, backtracking, sub-goal setting, and backward chaining. Crucially also for the self-improvement via reinforcement learning. Supervised fine-tuning is great. Do not forget about supervised fine-tuning with long chain of thought data, because they give you a high performance afterward if you do your reinforcement learning procedures. And an advanced reward shaping function in the reinforcement learning will even improve this performance. So, despite taking here seemingly different routes, both teams, Carnegie Mellon and all, and Stanford and all, converge now on a central insight. Structured reasoning is the linchpin of advanced problem solving in AI. And you know, structured reasoning, this was the main idea that I showed you here in my last video about reasoning flux from Princeton University. So again, Carnegie Mellon, Stanford, Princeton University, we all converge now on this structured reasoning for advanced problem solving. So nice. So the true power now of our hopeful future improved language model lies not just in more data, more input, but in how those models reason. If we provide here detailed specific patterns of reasoning, if you want, template structures that are not linear, that have multiple dimensions, that are, yes, of course, a graph structure, I think we can optimize here the performance of our reasoning LLMs and improve, of course, the correctness of the final answer. And you know, one side information, they even did this here, and they just provided the models with how to reason, and they provided in this how to reason some incorrect data. But the model learned on the correct form, but on the not so correct data, was able to come in other tasks to the correct solution, because the AI system understood how they should reason. What is the pattern, the reasoning pattern for them to follow in particular circumstances? So it was not the correctness of the single data points, but just tell me how to think. Tell me how to reason. This is what AI shouts to us. So you see, it is beautiful. Even a simple task like, hey, how can I improve my 3B local LLM? Gives us so many new ideas if you look at the AI research literature from just yesterday or the day before yesterday. And we can immediately start to improve our reasoning capabilities. And if you subscribe, you know, together we can find out what happens next week.